Hello and welcome to ENGR 330 Fluid Mechanics Recitation on Chapter 8. We are still doing Chapter 8. This would be covering the later half of the chapter to give you better understanding of the concepts we learned. So let's look at some problems from your book. Problem 857. To conserve water and energy, a flow reducer is installed, which is shown here in the shower head in this figure. If the pressure at point 1 remains constant and all losses except for that in the flow reducer are neglected, that means we have to consider the losses due to the flow regulator or reducer. You're asked to determine the value of the loss coefficient based on the velocity in the pipe. So based on the velocity in the pipe, you're asked to determine what is this loss coefficient. And if its presence is basically to reduce the flow rate which comes out of here by a factor of 2. So if you didn't have the flow reducer, this would be Q, but if you had the flow reducer, this would be reduced by a factor of 2. And you're asked to neglect gravity. Essentially they're asking you to neglect the elevation effects. Okay, so let's go ahead and look at this problem. Immediately you can see that we are interested to find the loss coefficient, which generally is related to the head losses and which is basically the minor head losses in this problem. So we should think of writing an energy equation. However, there is only one point right now mentioned on the figure. So let's go ahead and pick another point right about here, and let me call this as point 2. Okay, so if I go ahead and write the energy equation between point 1 and 2, I get P1 over gamma plus V1 square over 2G plus Z1 equals P2 over gamma plus V2 square over 2G plus Z2, and then we should consider the losses, where this would be the total head loss, the loss due to the major losses and the minor losses, but in this case we are only interested in the flow reducer losses, which would be as a result of the minor losses, which will incorporate the loss coefficient in the problem. Okay, and let me go ahead and write HL is KL V1 square, okay, which is the velocity in the pipe shower head over 2G. Okay, so let's try to identify a few things here. So at this point, we know that P1 is constant, but we really don't know what P1 is. Okay, so we don't know this. However, P2 is 0. Okay, Z1 you can neglect the elevation effects. Okay, and also we really don't know what is HL, or in the sense KL, and it also has another unknown. So we have to somehow get rid of this P1 and try to come up with an equation where everything is in one variable. So the way to do that is, since the pressure at 1 remains constant, if you had no flow reducer, we can go ahead and write the energy equation for that. So if no flow reducer, then you have P1 over gamma plus V1 square over 2G will be equal to V2 square over 2G. Okay, so that would mean that the solved for P1 in terms of rho over 2 times V2 square minus V1 square. Okay, this is density. Okay, so you have that, and then you can write your V1 as Q over A1, right? And you know the diameter of the shower head there, so you can put in the numbers and you'll get something like that. And then similarly V2, which is this guy here, you see that there are 50 holes of diameter 0.05 inch. Okay, so V2 will be equal to Q over A2. So if you simplify that, it will be Q over 50 times pi d2 square over 4, where d2 is 0.05 inches. So if you convert the units, you should get about that, which is twice of what you found earlier. Anyway, so now we can go ahead and write this P1 in terms of Q. So we can write V2 and V1 all in terms of Q. Okay, and you'll see the benefit of this at the end. Okay, so I can substitute everything here, and then I can get P1 is about 8.07 into 10 to the 5 rho Q square. Okay, I'll let you do the math here. Okay, so now in this equation we could come up with P1 in terms of Q. So you can see that V1 I can write in terms of Q, V2 in terms of Q. So you see where we are going with this. Okay, so the idea is you want to get your KL out of this, and you can see that V1 also you can write in terms of Q. So it will then become one equation and one unknown. You might think Q is still an unknown, but you'll see that it will get cancelled. Okay. Okay, so when you have the flow reducer, which is what would result in the loss coefficient, what's going on is you have your V1 will be half of what you would have without the flow reducer. So again, similarly V2 will be that. Okay, so substitute these into this equation. P1 over gamma plus V1 square over 2G equals V2 square over 2G plus KL V1 square over 2G. Okay, I'll let you simplify this. So write everything in terms of Q's. Okay, and you'll see that Q's get cancelled, and then your only unknown would then be KL. So if you do the math here properly, you should get KL to be about 9. Okay. Alright, let's look at another problem. Okay, the pressure at section 2, which is this main line here, is not to fall below 60 psi when the flow rate from the tank varies from 0 to 1 CFS, which stands for cubic feet per second. So you're given volumetric flow rate. And the branch line is shut off. Determine the minimum height h, which is this height, of the water tank under the assumption. The first assumption you want to make is, you're asked to make, is minor losses are negligible. And the second part of the question says minor losses are not negligible. So again, the basic idea is to try to come up with an equation which will have these head losses, which generally is our energy equation. So let's try to identify a couple of points in the system and then try to write an energy equation and see if we can come up with the losses. Okay. So I have point 2 here, which is the main line. So I'll put another point here and I'll call that as 1. Okay. It's right on the reservoir. So if I now write the energy equation between 1 and 2, P1 over gamma V1 square over 2G plus V1 equals P2 over gamma plus B2 square over B2 square over 2G plus Z2 plus HL, okay, which is the total head loss. Okay, so you can see that P1 goes to 0, okay, V1 is 0 and you know why that is. And for now, let's try to make sure this P2 is at 60 psi, okay, and let's pick our datum at Z2. So this is our datum and HL. So if you simplify this, you'll get 16 plus H equals B2 square plus HL plus P2 over gamma. Okay, and in this we know P2, we know gamma, we don't know V2, but we are given a flow rate. So let's take the highest end, which is 1 cubic feet. Okay, so Q is nothing but V times A, which is V2 times A. You know the diameter of the piping here, so you can get V, which will be 5.09 feet per second. Okay. So now the question is, what is HL? So we know that HL is due to the major losses plus contribution of the minor losses due to the different types of fittings. So we know that it's the major losses are F times L over D, V square over 2G plus sigma KL V square over 2G, and this sigma KL is based on all your fittings, so we'll just add them up and multiply with V square and divide by 2G. So for part A, they told you to assume the minor losses are 0. Okay, and also if you look at on the figure, they're talking about plastic pipe and flange fittings, and they gave you epsilon over d, which is relative roughness, equal to 0. So that means we're talking about a smooth pipe here. Okay, alright, so then we have to compute HL, so which would be just FL over D V square over 2G. Okay, so we know that F is a function of now Reynolds number and epsilon over D, but this guy is 0, so just calculate Reynolds number and you can do that easily, right? You know the velocity, you know the diameter of the tube, you know the viscosity. Okay, so you should get your Reynolds number as 2.1 into 10 to the 5. Okay, so once you have that Reynolds number, you can get F from the Moody diagram, which would be 0.0155. So let me write that, it's figure 8.20. Okay, so now we can substitute this into this equation here. and you see that the only unknown here would then be your h. Okay, and it will be one equation, one unknown. So I'll let you simplify that. You should get h to be about 143 feet. Okay. All right. So part B. Now we have to consider HL minor as well. Let's try to find sigma KL. So zero point 0.5. So you have a sharp entrance here. So if you look at the figure in your book, it will give you the entrance loss coefficient. So for sharp edge like this, it would be zero point 0.5, and you have 15 90-degree elbow fittings which are flanged. So go to table 8.2, it will give you zero point 0.3 as the value here, and you have a T here which is flanged as well. So if you include all of those, you get sigma KL as this. So all of these are flanged, and this is the sharp edge entrance. These are the 90-degree elbow, and this is the T, which are all flanged. Okay. Okay, so now you just substitute this by considering the total head loss here as this. Okay, and then you solve for h again. So h will turn out to be about 146 feet. So you can see that if you compare this and this, what it should tell you is the minor losses are not that significant in this particular problem. Okay, so all we did here was to identify a couple of points in the system and then write an energy equation, and then we could then get what we needed, and which is in this case which will be the height here, which turns out to be coming into the equation because of z1 and z2, and I picked z2 as my datum, and you can see that it's 6 plus 10 plus h, which is 16 plus h here. Okay, and you know by now how to do these kind of problems. Okay, so let's look at the next problem. At a ski resort, water at 40F is pumped through a 3-inch diameter, 2000 feet long steel pipe from a pond at an elevation of 4286 feet to a snow-making machine at an elevation of 4623 feet at a rate of 0.26 cubic feet per second. If it is necessary to maintain a pressure of 180 psi at the snow-making machine, you're asked to determine the horsepower required or the horsepower added to the water by this pump, and you're asked to neglect the minor losses. Okay, so let's consider this pipe here. So there's a pipe which is pumping, and there's a pipe which is going through a pump, right? And let's identify a couple of points here so that we can write the energy equation, right? So if I write the energy equation here, I get P1 over gamma plus V1 square over 2G plus Z1, and then you would have the head due to the pump, which will be a good thing to have, which will be equal to P2 over gamma plus V2 square over 2G plus Z2 plus HL. In this case, the head losses are only due to the major losses, so the minor losses are negligible, so we should compute those. However, we can neglect few terms. P1 is 0, V1 is 0, and we know Z2 minus Z1. We can just take the difference of the two elevations we are given, so that we know, and we can also compute V2, which will be the velocity in this pipe. So we are given a flow rate, so we can quickly do that. So all we have to do essentially in this problem is first to calculate these head losses, which will be due to the major losses. Before that, we have to compute V, which is Q over A, right? And if you do the math here, this should be about 5.3 feet per second. So once you have that, you know that the friction factor F is a function of Reynolds number and epsilon over D. So you are given a steel pipe. So go to table 8.1 and you can compute epsilon over D. So you pick the commercial steel pipe. So you can do this. I'm converting the 3 inches to feet. So I get 6 times 10 to the negative 4. And I can also compute the Reynolds number BD over nu, and make sure you use the viscosity of water at 40F from table B1. Okay, water, and you'll get 7.96 into 10 to the 4. So with this, you get F from your Moody diagram from figure 8.20 or your Moody chart. Okay. Okay. So now you have everything to compute HL. So HL, just substitute that in this guy here. Then you get HL as 74.3 feet. Okay. So once you get HL, you can see that in this equation, the only unknown will then be HP, which you can solve. So HP is P2 over gamma plus V2 square over 2G plus Z2 minus Z1 plus HL. So if you do the math, you'll get this to be 827 feet. Okay, but we are asked to compute the power. So W dot pump will be head due to this pump times the specific weight times the volumetric flow rate. So if you do it and convert the units to horsepower, so you should get this to be 24.38 horsepower. Okay, the only new thing is applying this particular formula, but you have seen this in chapter 5 when we talked about the energy equation. However, at that point, we were not computing head losses. We just took whatever was given to us, but now we are actually computing head losses with the knowledge gained in this chapter. Okay, this is problem 892. When the pump shown in this figure adds 0.2 horsepower to the flowing water, the pressures indicated by these two gauges are equal. We are asked to determine the flow rate. And you're given a bunch of information here: length of the pipe between the gauges, pipe diameter, pipe friction factor, filter loss coefficient. Okay, again, as we have been doing, if we are interested to do something like this, we probably would like to identify a couple of points here to apply the energy equation. So I'm going to identify 2 points here where the pressure gauges are located so that I I know that the pressures there are equal. Okay, so if I go ahead and write the energy equation, I get P1 over gamma plus V1 square over 2G plus V1 equals P2 over gamma plus V2 square over 2G plus V2 plus HL. And on the left hand side, because of the pump, we would have some head due to the pump, so HP goes on the left hand side. Okay, so you can see that you will get P1 and P2 over gamma, P1 over gamma and P2 over gamma cancel out, right? And you'll also find out that major the major losses in this particular problem are negligible. So you have to only consider the minor losses in the problem. And also V1 will be equal to V2. So the difference between those two guys goes to 0. So what you end up, and then Z1 will be equal to Z2, same elevation. So what you'll end up is HP is equal to HL. So that means if you calculate HL, you calculate HP. Okay? And we know that HL is the head loss due to the major losses plus the minor losses. So it's F L over D V square over 2G plus KL V square over 2G. Okay. Alright, so and then HP is equal to, we know that in the earlier problem we learned about this formula. HP is nothing but W dot over gamma Q, and we know W dot, which is zero point 0.2 horsepower. We know Q, which is the, or we want to find Q, which is the unknown. Okay, and make sure you have the consistent units. If you want everything to be feet, so make sure you convert the horsepower to feet pound per second. You can do that easily. So this should be 110 over gamma Q. Okay, so now I can write 110 over gamma Q because HP is equal to HL. Okay, should be equal to FL over D Q square over A square 2G. We're going to just write V as Q over A plus KL Q square over A square 2G. Okay, so you can solve, you know everything here, you know F, you know KL in the problem, okay, you know L, you know D, so you can solve for Q. Okay, and you'll get, if you do a little bit of algebra here, you get Q cube is 220A square over rho F L over D plus KL. This looks slightly simpler, so just substitute the numbers and take the cube root. And then you take the cube root of that, so Q will be 0.06 cubic feet per second. Okay? So this is how you go ahead and compute the flow rate in this particular situation. Okay, let's look at one last problem in this chapter. problem 96. The pump shown in this figure here, the pump, delivers a head of 250 feet to the water. Okay, so HP is what you're given. So try to see what you're given in terms of the problem. So if you're given the in terms of horsepower, that means you should be able to get the head of the pump, okay, based on the formula I've shown you previously, or you can also be given the head of directly. Okay, and if you're asked to compute the horsepower required in this pump, you can always do that if the problem is well defined. You're asked to determine, which is exactly I was saying, you're asked to determine the power that the pump adds to this water in this problem. The difference in elevation of the two ponds is 200 feet. And you can see that you don't have to really look up tables for the loss coefficients. So for the valve, for the entrance, and for the three elbows, in fact you have 1, 2, 3, 4 elbows, you're given the loss coefficient for those, and you're also given the exit loss here, okay, which is 1. Okay, so again we are interested in finding the power in this particular problem. It's a little bit involved, as you see would happen pretty soon in this problem, but we have to set it up. So let's try to make use of the fact that these are two reservoirs here. So I'm gonna identify point 1 and point 2 in the flow field on those reservoirs. So if I write the energy equation, I get P1 over gamma plus V1 square over 2G plus Z1 plus the pump head will be equal to P2 over gamma plus V2 square over 2G plus Z2 plus HL, okay, the head losses. So we can see that P1, P2 gauge, V1, V2 go to 0 as well, those are huge reservoirs, and we know Z2 minus Z1 is 200 feet, and we know HP, we have to find what HL is, okay? Okay, so the total head loss is again the major head loss plus HL minor. Okay, so in this problem, it's not given that you can neglect the minor head losses in this problem. So we should write this would be FL over T V square over 2G, and the minor losses will be sigma KL V square over 2G. Okay, so we should then identify what are the different fittings in the problem, and then write sigma KL. So as I said, you have 1, 2, 3, 4 elbows, and you are given that it is 1.5, and you have the entrance loss coefficient here, and you have the exit loss coefficient of 1, and then you have the valve loss coefficient here, which is 5. So if you put all those here, you get 0.8 plus 4 times 1.5 plus 5 plus 1, okay, that's here, which is about 12.8 v square over 2g. Okay, so if you substitute all these into this equation here, you'll come up with a relation between f and v. So let me write that relation. So you'll get 3220 equals 66.7 f plus 12.8 v squared. So at this point we have one equation and two unknowns. We really don't have a lot of information to compute v or f at this point. Okay, so this is where we have to think of doing the iterations. So we know that f is a function of Reynolds number. Okay. In this case, it's since in the figure we are given that pipe roughness is 0, this guy is 0, right? So Reynolds number is rho b d over mu. So if you do it, you won't get a specific number, but you'll get again in terms of d. Okay, so this is where you have to iterate. Okay, so you have to, so let's talk about a couple of methods. The first method, which is what you probably would have to use in your exams and when you don't have access to a computer. So what you do is you choose some f, let's say you pick 0.02, okay, and then you compute the velocity because you have a relation between velocity and f, so you can use this equation and you compute the velocity. Okay, and then once you do that, go ahead and compute what is the Reynolds number with this particular velocity, and then check what is the f from the Moody diagram, and you'll find that it is definitely not equal to what you selected before. So then you again choose f equals some other guess, okay, and then you compute the velocity, and then you compute the Reynolds number, and then at this Reynolds number for a smooth pipe, check what is the f you get, and it will so happen that they will both be reasonably close. So that means you have converged. So f is equals 0.012 is the solution with v equals 12.4 feet per second. So what we are interested in this particular problem is computing the power for the pump, so which is gamma q hp. You know hp, you know gamma. You can compute q, which will be v over a, which we just computed the velocity. So this should be about 155 horsepower. Okay. Okay. For those of you who are interested, there is another method to do this. If you have access to computer and if you're interested. So second approach, which would be ideal if you want to do some programming coding stuff. So you can write v in that equation in terms of f, okay, and I'm assuming you can do this math here, okay, and then you also can write Reynolds number, and there is a v if you remember. Now I can write that as 3220 over 666.7 f plus 12.8. Okay, then if you remember, we had the Colebrook formula. So I'll write the final simplification here, but I'll let you do this. So you can substitute wherever you see the Reynolds number, you can substitute all that I'm showing here is a simplification, but you can easily get at this. Okay, so you'll end up with something like this. Okay, you see that again, this is not that easy to solve. However, it is only in terms of f. So if you use some kind of iterative scheme, which I did, and then I got f to be 0.0122. Okay, so which is close enough to our initial guesses. So again, you'll end up with the same velocity. You can then determine W pump as well. Okay. Okay. So this is one of those problems where you have to do a little bit of iteration. Okay. So this concludes the recitation for chapter 8. This completes all the different concepts. So I would encourage you to look at the part 1 of this as well if you're preparing for the final. So looking forward to talking to you again. Good luck.